All right. Hello, everyone. Welcome back to Operating Systems. I hope that you have all had an excellent weekend. Hope that you had some chance to relax. I hope that other classes don't have more stuff due this week. I hope things are going okay. It is the last week of classes. I'm happy for that. I think we're probably all happy for that. I think we're all probably happy for that. Today is also appearing to be the last cold day for the week, which I am delighted about. I'm very happy about that. Today, there's a bunch of stuff here that last week I kind of mentioned spiritually continues to live in our learning outcomes for the week, and it continues to live, and I'm going to put it here explicitly again. I want you to continue to be able to discuss the benefits of partitioning memory and address spaces. So the last 2 weeks have been us looking at the introduction of virtual memory. So we're looking at base and bounds, and then we moved on to segmentation after we identified some problems with base and bounds. This week, we're going to be taking a look at another method for partitioning memory, which is paging, that tries to address some of the problems that we found with both base and bounds and with segmentation. Related to that, then, I want you to be able to explain how the entire address space for a process can be provided or supported via the concept of virtual memory. So one of the pictures that we're going to draw today is kind of like representing this is what our virtual address space is, and compared to our physical address space, it is immense. It is so unimaginably big that it's hard to imagine that we could fit any processes in our system, let alone having hundreds of processes in our system. So I want to be able to really fully take this idea of how do I get this entire giant massive address space and stick it into something that's much more constrained in terms of the physical memory that I've got. I want you to be able to describe how the operating system works with the underlying hardware to manage specifically now paging. So in the last couple of weeks, it's been base and bounds. There's a register that says this is where the address space for this process starts in physical memory, and this is how big it is. With segmentation, we did that same thing, but 3 times instead of once. So where we had different segments where they had different sizes, and we were just allocating those physical things in memory. We're going to start looking at paging, and paging is significantly more complex in terms of the structures that are necessary. However, from an operating systems perspective, the actual stuff that we're putting into this is conceptually fairly minimal. What we're ultimately going to be doing, and I don't want to give this away, but what we're ultimately going to be doing is instead of having 2 or 3 segments, we're going to have n segments, and they're all going to be the same size. And instead of having a pair of registers for each of those segments, we're going to have 1 register and then a big chunk of memory that describes the relationship between physical and virtual addresses. So I want you to be able to describe how an operating system works with this underlying hardware to manage paging, and really that's going to be the same overall big idea. Tell the hardware how to do these address translations. Give it the information it needs to do it. And then the new thing today is explain the operating system data structures and algorithms used to manage a partitioning strategy such as paging. We're going to take a look at paging. We're going to quickly find out that paging itself is not a feasible solution to the problem that we have. And so how do we address the problems that come with paging, even though it does seem to solve the problems that we were able to identify with base and bounds and segmentation. Before we do any of that, I promised that I would give you a chance to ask me questions about the final exam. And so I have a Mentimeter here. I'll hold this up for about 10 seconds. And then while you're starting to post questions, I will tell you a little bit about the final exam in terms of the structure that you can expect on the final exam. So I'll leave this up for a couple more seconds, and then I'm going to scroll down in my set of slides here. I'm also happy to answer questions verbally if you have questions verbally. So the exam is it's 1 week from today. It's at 6 o'clock. The rooms, I believe, have been scheduled, but I don't remember what the room is because I didn't look it up, so I never knew it in the first place. But I believe that we are scheduled in a room that has other exams going on in it as well, so we're not necessarily going to be in the room by ourselves, but it's at 6 o'clock next Monday. Frank Kennedy Brown Gym, thank you. But I encourage you to look the schedule up on your own to guarantee you know where you're going. The exam is going to be 2 hours in length. in terms of the time that we have allocated for it. The seating is going to be assigned in the same way that it was for the term tests, except it's going to be both sections merged together into one big blob, and then seating will be allocated randomly across that. I'm going to do the seating assignment, and you should expect to receive an email from me the morning of the exam that tells you what your seat number is. So I'm not gonna have that information available this week, but I will email you on Monday morning before the exam happens, so you'll have some idea of where to go when you get to the exam hall. In the same way that the tests had your name printed on it for the term tests, they will also have your name printed on them for the final exam. Please make sure you have photo ID that has the same name that's printed on the exam for when you're doing the sign-ins and stuff. The material for the final exam is going to be cumulative from the beginning of the course. This is a final exam, it's a comprehensive exam, and so it's going to have things that go all the way back to the very beginning of the course. However, the emphasis is on the second half of the course. You've already written one term test that deals with a lot of the stuff from the first half of the course, so most of what you're going to see on this final exam will represent the things that we've done in the second half of this course. Structurally, it's going to be similar to the first term test, or to the term test. So like in terms of the type of questions that you could expect to see, you can sort of expect to see the same kinds of things that are on the final exam. And similar to the term test, there's no programming. I'm not going to ask you to do any coding. You have been fully and adequately assessed on programming in this course, so I'm not going to ask you to do any programming on this test. I may give you code, and I may ask you questions about the code, but I'm not going to ask you to write C code because I don't want to read C code. I don't want to read C code. I'm going to pop over to my Mentimeter now, but again, I will be happy to answer any verbal questions that you might have. So the first question I've got here is, what are we expecting to know in terms of locking mechanisms like test and set, fetch and add, compare and swap, and ticket locks? For the first three that I got here, test and set, fetch and add, compare and swap, the key thing here is that these are doing atomic operations. That is the really key fundamental part of this locking idea with those things, is that they all do some kind of an update atomically. They get a value and they update or change that value in one single atomic instruction. And in terms of locking, that's the main thing that I really want us to be able to know about here. Ticket locks, fundamentally, they're the same idea. They enforce mutual exclusion. They are fair in a way that the other locks are not fair. They do require us to use atomic instructions to be able to accomplish things like increasing the current ticket number to allow the next thing to go into this thing. But the important part to me, and the part that makes me think that ticket locks are just really neat, is that they basically build a queue structure into them. They build a queue structure into them because we've got this idea of the first person to show up, the first task to show up to try and lock this thing is going to get a number that's lower than the next one that comes. And that's lower than the next one that comes. And that's lower than the next one that comes. So we're enforcing an ordering on the tasks as they show up in terms of being able to get access to the critical section. These other basic locks, spin locks that use fetch and add, compare and swap, test and set, these do not guarantee fairness. It's actually up to our scheduler to guarantee fairness with these kinds of locking mechanisms. If the scheduler is fair, then the lock is fair. If the scheduler is not fair, then the lock is not fair, and we can't know that this task will ever get to have access to that thing. Whereas ticket locks sort of guarantee fairness in and of themselves because they have this queue structure underneath. What are we expected to write in terms of pseudocode? Yeah, I am not going to ask you to do programming, whether it's pseudocode or C programming. I'm just not going to ask you to do that. So the main thing is going to be about, here's some code, tell me about it. Tell me what it does in terms of modifying data structures in the operating system that represent different parts of the operating system. Are there going to be questions directly related to the physical layout of hard drives, or is that mostly just so we understand choices with I/O scheduling algorithms? So, I mean, it's not unreasonable of me to ask you to label parts of a hard drive. It's not unreasonable of me to ask you that because that is one of the learning outcomes that's in the course, is to describe the physical structure of a disk. In terms of like me allocating points to something like that, it would probably be pretty low compared to other things because I want to do more high concept stuff as opposed to just memorizing the physical structure of a drive. The physical structure of a drive is definitely related to I/O scheduling algorithms, and it's also related to file systems. Again, remembering back to this idea of we've got this linear structure that we think about with file systems, but when we actually lay that out on a disk that has different platters, we've got more than one contiguous sector when we've got a sector that's on a track. All of the sectors that are in the cylinder that are contiguously next to that are going to be next to it. So this is, I guess, more tending toward the understanding choices with I/O scheduling algorithms as opposed to just recall questions about the physical layout of a hard drive. Any multiple choice questions? I haven't set the exam yet. I don't usually have multiple choice questions, but I'm not saying no. I say this to my children a lot. I'm not saying no, but I'm not saying yes. I'm not saying no, but I'm not saying yes. It's not likely to have multiple choice questions, and if I do have multiple choice questions, it's going to be a limited number of multiple choice questions, but they might show up. Is it more focused on topics after the midterm? Yes. So yes, you can expect the emphasis to be on topics after the midterm. In terms of like stuff that you might be looking at, what I would say is, in terms of stuff you might be looking at from before the midterm, I'd say look at stuff that you haven't already been assessed on. I'm not going to ask you questions on rate again. I don't see any value in that. I've already asked you that question, and I don't really feel like I need to do that again. But there were things from before the midterm that I didn't ask you about, and so those would be more likely to show up on a final exam than something that I did already ask you about. I'm not saying that I won't ask you about stuff I've already asked you about, but RAID specifically, I'm not going to ask you about RAID on the test. Yes. Yes, yeah. Yeah, okay. So the term test was too long. The term test was just too long. I mean, I'm going to be honest, it has been a really long time since I've taught 50-minute sections. It's been a really long time since I taught 50-minute sections, and the test that I gave you was better for a 75-minute section. Yes. So will time be an issue for the exam? I will be writing a 2-hour exam. I'll be writing a 2-hour exam, one that's intended to fit into 2 hours, and I will be very conscious of this when I'm building this exam. So I'm gonna try and say, I mean, time will be an issue in the sense that it normally is an issue for writing tests, but I'm gonna try to make sure that the exam actually fits appropriately into the time that we've got for this exam. No swapping, no swapping, no swapping. No swapping covered in the course, so don't worry about swapping in terms of learning outcomes. Is the final harder than the midterm? I mean, I don't really know how to answer that question directly. It's similar to the midterm in terms of difficulty, I'd say. I mean, the topics that we moved on from file systems are less of kind of like mechanical, this is what file systems look like, to more abstract. There are moving parts in the stuff that we're doing now with scheduling. But I don't know if I can say one way or the other if it's harder or easier than the term test. And that's it. That's the last question. All right. Are there any verbal questions in the room? All right. Awesome. Okay. I'm happy to answer more questions about the final exam. My strong preference is for you to ask those questions on the course forum if you're going to ask them, just so everyone has access to the same information. Generally, when people ask me questions about the final in my office or ask me by email, I will just politely direct them to the forum or to this opportunity here. So if you do have any more questions about it, please ask those questions in the course forum. I hope that this is helpful in terms of getting going with the final exam. But if there are no other questions, then let's move on and start talking about paging. So we've seen two different mechanisms for implementing this idea of virtual memory and mapping virtual address spaces to physical memory. The first one that we were taking a look at was this idea of base and bounds. Base and bounds partitions physical memory. We are separating physical memory into fixed size partitions, and then we're putting entire address spaces into those fixed size partitions. Generally, this means that we're making our address spaces quite small compared to what we have available to us on the architecture that we're using. But the main problem with base and bounds was we have this idea of internal fragmentation. We're allocating this entire address space. We're putting this entire address space into physical memory, and there's this big chunk in the middle that has been allocated for a process to use, even if it never actually uses it. And a lot of the time, it does not actually use it. So if we did base and bounds with, for example, my terminal software, it is unlikely to use an 8 GB virtual address space. It's unlikely to use anywhere near that much memory. Chrome might, but my terminal is not going to do anything like that. And so for most processes, what this means is that we've got this stuff that's allocated and unused and thus unusable. I cannot put other processes into that space that's between the heap and the stack for different processes. And so we've got internal fragmentation, and that's bad because we're kind of wasting a bunch of memory. We then moved on to segmentation, and segmentation tries to address this specific problem of internal fragmentation. Rather than allocating the entire address space, let's segment the address space. Let's partition our address space into fixed size partitions. And then of those fixed size partitions, I'm only going to allocate as much as I am currently using in that partition. So in our textbook, we describe this as 4 different segments. In practice, it's 2 different segments, the code heap or the data section, and then the stack segment. And we allocate only as much of that as we're actually using. Our process now has access to 64 bits or n bits, whatever kind of architecture you're using for its entire address space, but if my stack is only 15 kilobytes in size, I'm only going to allocate 15 kilobytes of physical memory for that segment. I'm not going to put that entire thing into memory. The big problem with segmentation is that while we have solved internal fragmentation, we are no longer allocating memory that is not used by the process. We're only allocating as much as is actually necessary. By allocating only as much as is actually necessary, we're introducing external fragmentation. These things that we're putting into physical memory are differently sized. Different sizes of allocations in physical memory will lead to situations like, in sum, there's this much physical memory available, but none of the slots that I've got in between all of these different allocations are big enough to actually put a new allocation. And so I have lots of free space, but my free space is unusable because I cannot actually put anything into there. And then we get into this complexity of the Comp 2160 compacting garbage collector assignment of, do I squish everything up to the top of memory? Do I defragment memory so that I have one contiguous free spot to put things in? And that becomes troublesome and problematic and expensive to do anything with. And so segmentation also has problems that we really don't want to deal with. But both of these are actually good ideas. Partitioning physical memory into fixed size spaces and partitioning our address space into fixed size spaces and then only allocating as much as we need are really good. They're great ideas. And so paging takes this idea, and instead of saying, let's just partition one or the other, it says, let's partition both. Let's partition both. I'm going to partition my physical memory into page frames. Page frames, the term here is I'm going to stick something into this. So it's a frame because it's allowing something to be stuck into it, like a picture frame. I'm going to partition my physical memory into page frames. Conceptually, this is fully identical to base and bounds, except it's much, much more granular. Instead of allocating a quarter of memory, I'm not going to allocate a quarter of memory. I'm going to allocate about 4 kilobytes per page frame. So every page frame is the same size. I'm going to partition physical memory into page frames, and then I'm also going to partition my virtual address into pages. Pages go into page frames. So I'm going to have this abstract idea of a page, and it's going to be put into physical memory page frames themselves. We are now going to have to start thinking about this idea that we have this internal representation of what the address space layout looks like, but it never actually physically materializes like that anymore. Virtual memory in our minds does not match anything like what's actually happening with physical memory anymore. From our processes perspective, yeah, it still has this layout, but it doesn't actually look like that. I'm going to partition physical memory into page frames that are about 4 kilobytes in size each. I'm going to partition my address space into pages that are about 4 kilobytes each. And the size of these are intentionally the same. I'm going to put my pages from my virtual address space into physical memory, and thus they have to be the same size. This means some things, like there are way more virtual pages than there is physical memory page frames. There are way, way more virtual pages in our virtual address space than there are page frames. But kind of like segmentation, we're only going to allocate page frames for the pages that we actually use. I'm only going to allocate as many page frames as I actually need to allocate. Let's draw a picture of this. So I'm going to pop over to my tablet here, and what I've got here is a representation of physical memory on the left side and virtual address space on the right. The textbook authors, they do the right idea of making this smaller when they're thinking about it, so like 16 kilobytes of memory or like 64 bytes of memory, but I would like to think about this in terms of a more realistic idea of what we have for physical memory and our virtual address spaces. So the idea here is that I want to take the physical memory that I've got, and I want to partition this into 4 kilobyte pages, page frames. So I'm going to have these different partitions of physical memory. The physical address space that I'm looking at here is 32 gigabytes in size, and it's quite large compared to 4 kilobytes. It's quite large compared to 4 kilobytes. And so the diagram that I want to draw here is kind of going to be a little bit zoomed into what we've got for our physical memory structure. The structure that I'm thinking about when I'm thinking about taking my physical memory and partitioning this into page frames is that we're going to be doing this partitioning into fixed sizes. And each of these entries here is going to be 4 kilobytes in size, 4 kilobytes in size. I'm going to be also taking my virtual address space, and I'm going to be partitioning that. I'm going to pick a spot that's way down here close to the bottom, because what I want us to think about here is the stack itself in my virtual address space. So this is my virtual pages. These are also going to be partitioned into 4 kilobyte partitions. This is 4 kilobytes in size for each one of these pages that I have in my virtual address space. And ultimately, what this actually looks like internally is that my virtual pages here are actually written into page frames in physical memory. My virtual address space here is virtual. It's really hard to think about this. It's really, really hard to think about this because, like, for 2 years, we've been thinking about how this virtual address space, this is just how it's laid out. This is the structure. But even with segmentation, we've broken that a little bit. It's still kind of the same. We still have parts that we expected to be there, and they're showing up in physical memory. But now we're doing stuff like taking this very granular partition of my virtual address space and sticking it into physical memory in different locations. There's a really big problem with this whole setup immediately. And the really big problem is that my physical memory structure here is limited to about 32 gigabytes in size. And with a 64-bit address space, I'm going to say that my physical memory might fit. No, that's too big. Sorry. My physical memory might fit this much of my virtual address space. I cannot even fit like a tiny sliver of the virtual address space that I've got into physical memory. The idea that we've got with paging here is that I'm going to partition this virtual address space into these fixed size partitions that are all the same size as what I've partitioned physical memory into. And I'm only going to allocate as much as I'm actually using right now. So in my virtual address space, I'm still going to have structures like a code and data segments. And now I'm drawing these wildly out of proportion here. I'm still going to have a code heap section. And I'm still going to have a stack way down here at the bottom. I'm still going to have a stack way down here at the bottom, but I'm only going to allocate as much pages as I actually need to represent the stack. And I'm only going to allocate in my physical memory then as many page frames as I actually need to represent the pages that I've got in my virtual address space here. And so the relationship that we've got is that we're going to have this abstract idea of a virtual address space, and we're going to have this abstract idea of virtual page numbers that represent where they're actually located in the virtual address space. So virtual page number 0 is all the way up there at the top, and then virtual page number 64-bit divided by 4096 bytes worth of bits is way down at the bottom. The structure internally to the OS that I'm going to be using to represent the relationship that I've got with these arrows here, mapping these things into my physical memory now, is going to be called a page table. We've seen the word table in a few different places, notably the open file table. That's the main place that we saw the word table. And when we were thinking about the open file table, we were thinking about things like, this is an array. It's an array, and the file descriptors that we get back to this in this array are indexes into the array that represent different parts of the thing that I've got. The page table structure that I have in my OS is something that I'm going to have per process. So every process is going to have its own page table. The page table structure is going to represent virtual page numbers. So each of the pages that I've got up here have a page number. I'm going to call this one M. This is M plus 1, M plus 2, plus 3, plus 4, plus 5, plus 6, plus 7, plus 8. So every page in my address space has a number attached to it. My page table is going to be indexed by these page numbers. And the mapping that we're going to have is to a physical frame number. So here we've got, this is the virtual page number, and the physical frame number is going to be up here. This is where this actually lives in physical memory. And so these are going to be labeled things like N, N plus 1, N plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. For these two entries that we have in our virtual address space here, we're going to have entries that are like, this is M plus 6 and M plus 7. These are going to be mapped into N plus 1 and N plus 2. So our page table here is going to be this array that represents page numbers in our virtual address space, and it will have a mapping to the physical frame number where that is actually stored. M plus 8 here is going to be an entry that doesn't have a value. It's not allocated by this process. We've only allocated 2 page frames for our stack, and so I'm just going to leave this as like nothing. It's not been initialized. There's nothing here. I'm going to put this back up in a second, but these entries here, these are page table entries. The acronym here is PTE, page table entries. Page table entries are something that we as an OS are responsible for populating. This is going to be part of our process control block. Every process will have its own page table, and we have the responsibility of putting a page table into memory and then filling up the page table for that process. And what we are going to tell the hardware is, we're going to tell the hardware what the page table's base location is, where the page table starts. This is the page table base register. With base and bounds, we were telling the hardware, this is where the virtual address space starts. This is where the segment starts. With paging, we're going to be telling the hardware, here's where the table of mapping starts. The hardware has to know what the page table entries look like at this point. So I'm going to come back here in a second, but I wanted to pop over to this tab right here. This is a document that's produced by Intel, and I will let the 5,000 pages scare you here. This is a massive document. This goes all the way back to like the origins of the x86 architecture, all the way back to like the very beginnings of what x86 looks like. So Intel 64 and 32-bit architectures here. This document describes everything about the hardware. This is everything that you'd need to know about the hardware to do things like build a compiler, and to do things like starting to build operating systems to work with this specific architecture. This document I'm going to search for the words page table here, and there are 155 matches. Most of them are like random things like this, like page and then table showing up on different lines. But there's also going to be page table entry descriptions here, and page directory, which is another structure that we're going to look at in this course. And I'm going to click on this reference here because it takes us down to about page 3000 in this document. And kind of similar to this documentation that we saw with exFAT, this describes the bit layout for what a page table entry should look like. In this case, it's a page directory entry that references a page table. We will talk about this very shortly, but this describes the structure of what this thing should look like. And so from an operating system's perspective, we have to know about this document so that we can structure this entry correctly for each virtual page number that we've got in this system. Paging is great from an overall idea because we've eliminated external fragmentation. With this, our page frames are fixed in size. Our pages are fixed in size, and they are exactly the same size. And with base and bounds, that was great because we could just look and say, hey, is this allocated or not? And then just find one that's free and we got something. We don't have to worry about shuffling anything around. We allocate these pages and we can use data structures like bitmaps and allocation structures to determine whether or not this page and page frame have been allocated from the operating system perspective. External fragmentation is solved. We did it. Great. Excellent. Internal fragmentation is minimized. We cannot eliminate internal fragmentation. We cannot eliminate internal fragmentation. I might be in this state where my stack structure that I've got actually allocates about that much of a page. Let's say that it's 10 kilobytes in size. My stack is 10 kilobytes in size. Still have to allocate an entire page to that stack entry. I can't have half of a page entry for that thing. But the difference between base and bounds and paging here is that I've sliced memory so thin, so thin, that even allocating that tiny bit for that stack, and even though nobody else can actually use it, who cares? Who cares? We're talking about 2 kilobytes of memory not being able to be used as opposed to an entire region of the address space being unusable by other processes. So external fragmentation is solved. We have accomplished that because everything is fixed in size. We either have something free or we do not have something free. We don't have to look for things by doing linear searches. Internal fragmentation is minimized because we are slicing things so thin compared to what we were doing with segmentation, with base and bounds, sorry. But this is still problematic. Paging still has a couple of major problems. The first, and one of the things that I didn't really illustrate in this picture, is that we have to put these page tables in memory. They don't exist in some other magical location. Just like the operating system has to live in memory, page tables have to go in memory. And in fact, page tables have to go in page frames. Yeah, so let that blow your mind for a second. Our operating system, when we were thinking about base and bounds and when we were thinking about segmentation, I was doing stuff like this. The OS is just going to allocate this part up here for its own data structures. But in practice, the operating system itself uses paging for itself. It doesn't allocate this big blob of memory and say, this is me. It allocates pages when it needs to allocate pages in its own address space. And it does things like allocating physical frames to represent processes and process control blocks for our operating system. And so that means that the page tables and the page table entries themselves are also within pages. And that means that we tell the hardware, where does this page table start? Process gets context switched on. We tell the hardware, this is where the page table starts for this process. The process begins to execute instructions that are referred to by its program counter in its virtual address space. The hardware has to translate the virtual address of the program counter into a physical page number. And so it first has to go to the page table base register and find out what that is, go to memory and find that page table entry in the page table for that entry, for that address, do the translation, get a physical address, and then go back to the process and load it from memory, that instruction from memory, so that it can actually begin to execute the instruction. So every time I need to do a translation here, I have to load an entry from memory so that I can do the translation, so that I can go back to memory and load the thing that I'm actually trying to get out of memory in this structure. And that's kind of painful. And this is actually solved by a structure that's called a translation look-aside buffer. This is a chapter in our textbook, but I believe personally that this fits into the computer organization course than it does for us. The translation look-aside buffer is a cache. If you're thinking about caches like L1 and L2 caches in comp.org, the translation look-aside buffer is a cache, but for address translations and page table entries. So it will have the same sorts of things as like least recently used as an eviction policy for when you're loading things in and out. But because we can put parts of our page table into this cache, we can address the speed issues that we have with paging itself. The size issues are kind of where we have a little bit of a problem. The size issues are where we have a little bit of a problem with this. And so I want to do some calculations here kind of quickly about 64-bit address spaces and 4 kilobyte pages. So I'm going to pop back to my tablet here. And I'm going to start to write this expression out. We have a 64-bit address space. We all agree on that? I think, yes, we all have a 64-bit address space. And that means that in terms of things that can be, bytes that can be in our address space, we're raising 2 to the power of 64. This is the number of addresses that we have in this address space. When we divide our address space up, when we're partitioning our address space into 4 kilobyte pages, we're effectively saying that I'm going to do minus of log base 2 of 4096. Do we all agree on that? Do you remember what logs do with base 2 and stuff? Yes? Some of us, yes. Some of us not wanting to shake our head, no. Very briefly, remember that we can do subtraction for representing division with log arithmetic. So I'm already in this base with 64 here. So when I do log base 2 of 4096, I'm trying to calculate what the exponent of 2 to the power is to get 4096. And so I can then subtract from that 64, subtract that from 64 because we're already operating in the same base here. So this is 2 to the power of 64 minus log base 2 of 4096. This is going to give me the number of pages that I have in my address space. This is the number of virtual page numbers that I've got in this system. The page table entries that we've got, and I'm going to pop back here to this multi-thousand page document. These ones are 32-bit page table entries, but in our modern systems, we've got 64-bit page table entries. And so they're going to be 8 bytes in size. we might have a bit of a problem here. We've got 64 minus log base 2. Can I do this? Oh, I didn't practice this. You know what? This is ridiculous. I'm going to start a spreadsheet because this is where I practice doing this. And so this is what I'm going to stick to here. I'm going to make this much, much bigger so that we can actually see the one cell that I care about. We've got here 64 minus log, and what I want is 4096 to the power of 2. So we have a total of 52 bits left, 52 bits worth of virtual page numbers in this system. 2 to the power of 52 is a very big number. It's a very, very big number. 2 to the power of 52 times 8 bytes per page is 3 to the 16 bytes. 3 to the 16 bytes is 3 to the 13 kilobytes. Is that many megabytes. Is that many gigabytes, and you kind of get the point here. This is one process. I haven't even gotten to having other processes in my system, and I have exceeded the physical memory that I have for this page table by orders of magnitude. Oh no. That can't work. It can't work. It cannot work. It cannot possibly work. I can't actually have pages that are like orders of magnitude. I cannot have page table sizes that are orders of magnitude bigger than physical memory. I can't do that. These are orders of magnitude bigger than disks. I can't do that. But most of my address space is not even allocated by the process. We noticed that before when we were talking about base and bounds. Most of the address space for my process is not actually used by the process. We have just moved internal fragmentation from the entire address space to the page table itself. So now we have this like million gigabyte size page table where almost all of them are invalid entries. They're not actually allocated by this process. They're never going to be used by this process. We've got parts at the top and parts at the bottom that are our code heap section and our stack section, and then lots and lots of virtual page numbers in the middle that are never actually going to be used by this process. So we've just moved internal fragmentation from our physical memory to our virtual memory. Both of these problems, where we've got a huge page table, and then we've got internal fragmentation within the virtual address spaces that are represented by these page tables, can be addressed by using a different data structure entirely. And that different data structure is called a page directory. Partitioning memory solved external fragmentation. We did that. We did accomplish that. We no longer have to look for free spaces by doing linear searches. We just use our bitmap and find a bit that says that this is free. And it minimized internal fragmentation of the virtual memory that we were actually allocating. So the idea with a page directory is, if we could partition memory and solve these problems, then let's partition our page table. Let's apply this idea recursively. Let's take our page table itself and partition that, and only allocate as much of it as we're actually going to use in this process. Let's partition the page table. Let's talk about file systems. Let's talk about file systems. Paging and file systems are, on the face of it, very different. They are very different. They're totally different memories, different levels of the memory hierarchy. And they're also dealing with the different kinds of data. Like, file systems are usually dealing with persistent data. I care about this information. I need it to stay there when I turn my machine off. Whereas paging is dealing with memory, and usually that's ephemeral or volatile, or like when my machine turns off, it's gone, and when I turn it back on again, it loads it all up again based on the state of the machine as it's running. But they are similar. And I'm not going to do this because we've run out of time, and we'll finish this next class, but they are pretty similar. And I want to start by taking a look at this file, maps, which we've spent an enormous amount of time looking at, really. But now we're going to start to be able to see some connections between file systems and paging. So at this point, we're continuing with all of these things. You should be able to discuss the benefits of partitioning memory and address spaces. You should be able to explain how the entire address space for a process can be provided and supported via the concept of virtual memory. You should be able to describe how the operating system works with the underlying hardware to manage paging. So now we've got this page table base register and the idea of page table entries being dictated to us by the hardware, and we as an operating system have to conform to that. And now you should be able to explain, at least initially, this idea of a page table. So explaining the operating system data structures that are used to manage a partitioning strategy such as paging. That's it for today. Like I said, next class, we'll finish up this page directory stuff. And then I will do a review. So if there are specific things you want me to review, I'm planning to do the review in form of Mentimeter because it's fun and it's something to end the class with. If there's something very specific that you would like me to have questions about, please email me by the end of the day tomorrow so that I have time to put some slides into the Mentimeter to deal with that.